So we left off talking about this loop over here doing our Kirchhoff law. So the voltage across here is the Q per C, the V sub C, minus the IR, because we're just doing the single loop by itself. Then for our second equation, doing our Kirchhoff stuff, we're going to use this outside loop, where there's the electromotive force from the battery. There's your first drop. It's an I times 2R. And then minus this drop on the outside. So we have the same current here and here because it's been closed for a long time. Been closed for a long time means this is fully charged as this going to be. So there actually is no more current flowing in this direction over a long period of time. So now if we put those together, this solve for this one first. It is the same I because there is no current going this way. So for this equation simplifies to the I for there, and it's going to be the same I as this over here. We can substitute that in, and so as we substitute that in for the I, finally we end up with bam, there you are. Okay, so the charge on that thing, this is the, remember this is your, you take the capacitance times the EMF, that is your charge. But it's divided by 3. It's not fully charged because remember there is a pretty big drop in potential right over here, so it's not the same potentials across the battery. Alrighty, so now this switch is opened over here. In this case, switches are originally opened, they're both open. Capacitor is uncharged in this situation, and then switch S1 is closed. Well, if you remember, the first thing that happens is you get a surge, and you get the full current going through like this isn't even there. Okay, so if you're doing for this particular diagram with this one being open and only this, well, you only have one loop now, so you don't need a lot of you don't need one equation. So that's the EMF in the battery. This is the drop across this resistor over time. And then this would be the the voltage drop across the capacitor as that thing starts storing up energy right over here. So immediately after you close the switch, we start off with no charge on the capacitor because it's uncharged. And so if we want to find out exactly what the current flow is, well, we don't have any, this right here, we don't have any potential across here. That's just the 0. So all we have left over is this right over here to find the current. Okay, but after a long time, there's no current that flows whatsoever. As this thing is fully charged, there is no current flowing at all when the capacitor is fully charged. And then we don't have any flow whatsoever, so this is actually a 0 flow through there over a long period of time, and that's all we have. Meaning that your EMF across your battery in this particular case is the same thing as the EMF across your capacitor, so they equal each other. Okay? So remember, this is your maximum charge at infinite time. Not infinite charge. Not infinite charge, it's an infinite amount of time. When you're fully charged, per the capacitance, it's the same potential. Okay, now when we talk about intermediate, between 0 time and infinite time, as this charges, well then the flow is going to get smaller and smaller and smaller until you're at full capacity over here. So your current is changing over time, your charge is changing over time, and that means your potentials across this is changing over time. So it gets a little more complicated. And so what happens is it's actually a logarithmic function. Okay, so what happens if you notice here over time, you don't have any charge stored on a thing, and at an infinite amount of time, it's finally fully full at some time later on. But as you put more and more charge on there, you get a back potential. More and more charge on there, back potential, you get less and less charge. It takes more and more time. That means your current is actually decreasing. Because if you remember, your current's at a maximum at the start, then it drops off. It's going to drop the other direction. It's going to drop the other direction, and it's going to approach 0 eventually. So it's going to look kind of like the opposite of that curve. But you notice this is a logarithmic thing that happens. So as time approaches infinity, your total charge is the same amount as the maximum charge you can get on there at that using that potential from that battery. But the current does just the opposite. That's why it's not the 1 minus the logarithmic function because the current actually is going to drop over time. The longer the time, the smaller the current you have going here. Here, since you're subtracting from 1, this is going to get smaller and smaller. We're approaching the 1 or the full charge over here over a period of time. Okay, so now in this case, now let's do the opposite. So now let's say we're opening this, but we're closing the second loop. So remember, we're fully charged. We just fully charged the thing with the same EMF that we had over here. So now we only have this loop working, and now this is the voltage source over here, and we have a current running through here, and that's it. So just after you close the switch, you have a full, whatever potential that is, same as the battery over there, that's when you're going to get your greatest current flow. But over time, as you're losing charge, that means your potential is going to drop lower, 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 the less charge you have. And that means there's going to be less flow over time till eventually there is no flow over time when there's no net charge left on these plates. So, but as the capacitor is fully charged, and as soon as you close that thing, you're going to get a full charge, you're going to get the full current going through there. So this represents the VC, the voltage across the capacitor, the charge per capacitance. This is the current, because remember we picked the direction of the current, and this is running opposite direction of the current, so that's why I ended up with a positive over here. And that sums up to find the solve for the I. It's just your Q over this RC. We're going to talk more about that RC in a moment. It's a time constant. This is a specific amount of time. And what that means is that depending on the size of the R, with less resistance, that means that's going to move this line this way. Because with less resistance, we're going to start losing charge faster. Or with more capacitance, that means you storing more charge. It could also change the amount of time it takes to drop. So more on this RC thing here in just a moment. Okay, so it solves out to be the current is your charge at the start divided by your RC. That's going to be how much current you have flowing. All right, so after a long time, remember that current you have, it drops down to 0. The capacitor is discharged, acts kind of like a wire at the very well. It's still going to have a potential across the thing. But after a long time, there's going to be no charge stored on that thing whatsoever. So there's no charge left over on the thing after a long time. But once again, the intermediate between the full current flowing for whatever charge you have initially on there and the 0 current later on, as you completely lose all your charge, it's going to look like this. So over time, you're going to have less and less and less charge on that. It's going to drop down like so. And the current is going to mimic that. Because the current is your charge per time. It's just you're losing that over time. So the RC is going to represent your time constant, or it's related to how long it takes to get to this value here, which in a moment we'll learn is we've lost 63% of the charge. Here we've lost 95% of the charge. Here at 3 of these we just lost, I think it's like 98, 99, about 99% of the charge and so on. Alrighty, so what is this time constant? That's a little tau. Okay, we're out of T's. We use T's for other things. But it's the time constant of how long it takes to get to a specific number. So when we find out what that RC is, because remember, we're related back to this RC over here by how long it takes to run out of juice. So, given a capacitor starting no charge whatsoever, the time constant is the amount of time for the circuit, the RC circuit, to charge a capacitor to 63% of its value. 2 RCs is going to be like 95 and so on. It's a logarithmic thing. So solving for the Q, you get to the 0.632. That's the percent of the things charged over time. Okay, so the time constant is the amount of time that the RC circuit takes to discharge a capacitor by 63%, because it works both ways. Okay, whether you're charging or discharging. Charging is the 1 minus, discharging is that because you're getting less and less charge. Alrighty, so pop quiz here. Time constant demo. Each circuit has a 1 farad capacitor in the thing, and it's charged at 100 volts. We have the same energy that we're starting with. So when the switch is closed, which system is the brightest? Well, it's the one that has the least resistance, which is of course number 2 over here. Which one will stay on the longest? Well, that's the one with the most resistance because it slows everything down. Okay? And which consumes more energy? Well, remember, we have the same capacitor charged to the same potential. It's the same energy. One just runs out, uses the energy much faster than the other one. So it's got a greater power over on this side over here than this one over here, but it's actually the same energy. Okay, so what happens with the time constant, because we have a lot less resistance, we have a quarter of the resistance that we have over here. It's literally a half resistance in 2R. It's a quarter of the resistance. It's got a different time. It's going to last for a quarter of the time till it hits down to that 63%. All right, so summing everything up here in 4 minutes. So charge and capacitors cannot change instantly. It takes time for that charge to come off of there. But it depends on 2 things. 1, your capacitance, and 2, the resistance of your circuit. So short-term behavior of capacitor. If you start out with no charge whatsoever, it has no potential difference across, it acts as a wire. Capacitor starts with a charge, it has a potential difference, and it acts more like a battery. The long-term behavior of the thing, current through a capacitor eventually goes to 0 as you're charging the thing up. If the capacitor is charging and fully charged, no more current can actually flow, and it acts as an open circuit. If a capacitor is discharging, potential difference goes to 0, and then finally no current will flow over time. In the intermediate behavior, that's when you got to mess with this stuff, the time constant, the RC, okay, because it's an exponential function. So calculate the current immediately after the switch is closed here. All right, so we have our values, 10 ohms, 30 microfarads, and 20 volts. So if we wanted to find the current right after the switch is closed, well, remember, it's like it's not even there. So this is no potential whatsoever at the very beginning. So that's the 0. So if you want to find out what the current is, it's just the EMF divided by the R. That is the 20 volts divided by the 10. And that would be just then 5. Okay? 20 volts divided by 10, that would be 2 amps. All right, calculate the current after switching close for 0.5 seconds. Now we're intermediate. Now we have to do a time thing. So the time thing is whatever the initial current is, which we just found it to be 2 a moment ago. Okay, it's going to vary with the time over the RC. Well, the RC is simply 10 times the 30 microfarads. So 10 times 0.03. So 10 times 0.03. So we got our 20 divided by 10. That's our initial current flow, the EMF, the E over the R, then to the exponent, and badam, 0.38 amps. So it was 0.5 at the beginning, but half a second later in this circuit is 0.38 amps. If you want to change that amount of time, you change either the resistance or the capacitance. Well, if you're not physically changing the capacitor, it's probably a lot easier to change the resistance. Calculate the current after it's been closed a long time. Well, guys, after a long time, this is fully charged. There is no current flowing. That's a 0. Okay, calculate the charge capacitor if switch has been closed for a long time. Well, that's just the full charge. So there is no current running, it's just the full charge. So if you want to find out what the full charge of the thing is, all you have to do is take your voltage times capacitance. And that's what your maximum charge is going to be in this particular circuit. Alrighty, so challenge. I know you guys like the challenges. So after being closed for a long time, the switch is opened. So this has been closed for a long time, then it's opened. So, hey, what happens to this thing? Well, this was charged. Now it's going to discharge by running through this whole thing. What is the charge left 0.0 seconds later after it's been opened? Well, we're discharging, right? So we're discharging the thing. So we're going to find out the amount of charge left. We have our time is 0.6 seconds. The R and the C. The R is the 2. The C is 15 millifarads. So 0.015. And remember, be careful about that R. It's 2R, so it's actually 4 ohms. Okay, 4 ohms and times initial charge. So it's the 0.368 is the amount of charge on there. Alrighty, 30 seconds left. Calculate the charge of capacitor this much times. So it's a whole new thingy. And now we are finding the charge after we're charging the thing. So now we're charging the thing. So it's a different equation because we're charging the thing. And we just plug everything in. And it's going to be 0.78 of the maximum charge, which is after the switch has been closed for a very long time. Okay? And so to find out what that amount is, it's just your EMF times the capacitance. And then the total times your 0.78, there you go, that many coulombs.